Good day, worldwide university students. Welcome to the channel of Massive Quality Mathematics, where we abuse mathematics by finding solutions. We are continuing with our videos of linear algebra concept. Today, I want to take you through the subtopics called subspaces as projected on the screen. So if you haven't yet subscribed to my YouTube channel, please press the subscription button and notification bell so that whenever I post my videos, you'll be the first to get notified and to watch. So let's get into it. So we want to talk about subspaces. Bear in mind that since we talk about vector spaces, examples of vector spaces, and verifying some vector spaces, just know that it is possible for one vector space to be contained within another vector space. It's very possible. In other words, if we have got a vector space V and a vector space W, it is possible that V can be contained within W. In other words, now we can have a vector space V strictly contained inside vector space W. That means that it is possible for one vector space to be contained within another vector space, and this is required to be proved. So let's talk about the formal definition of a subspace. So a formal definition: if we let V be a vector space, then the non-empty subset W of V. So the non-empty subset W of V. In other words, now this V is a vector space and there is a non-empty subset W of V is said to be a subspace of V if itself, we know that if there's a non-empty subset which is W of V, that means W is inside V already. So that's what, and it's non-empty. So it's non-empty, that means inside W there's something. It's a set with something. So then the non-empty subset W of V is said to be a subspace of V if itself it's a vector under the same vector addition and scalar multiplications. So this means that, now it means that this W, the non-empty subset W of V, is said to be a subspace of V if itself is the vector, under the same operations of vector addition and scalar multiplication. So this is a simple definition of a subspace. So now let's go to the theorem that we're going to use. The theorem that we're going to use to prove this is the theorem. So now let's see what the theorem states. So the non-empty subset W of V is said to be a subspace of V if and only if the following condition holds. So this is an explicit meaning of what do you mean when you say non-empty subset W of V is a subspace of V. So this non-empty subset W of V is said to be a subspace of V if and only if the following conditions hold. What are those conditions? So these are the conditions. The first condition, W must be non-empty subset. So W is non-empty subset. In other words, W contains a zero vector. It contains something. So W is a non-empty subset. That is, W contains a zero vector. So if a vector U and V belongs to W, then the combination, the sum of the two vectors also belongs to W. This is a closure property under vector addition. So if we have two vectors, individual independent vectors inside W, then the sum of those two vectors must also be inside W. And we talk about the closure property under vector addition must be satisfied. So if K is a scalar and belongs to real number, is any scalar, and U again, it's a vector belonging to W, then KU must also belongs to W. That means this scalar multiplication of K and a vector U must belong to the W. This is a closure property under what you call scalar multiplication. This is a closure property under a scalar multiplication. So this is a closure property under scalar multiplication. So this is the theorem. So in order to say a non-empty subset W of V is a subspace of V, W must be non-empty. If there is a vector U and V inside W, then the sum of those two vectors must also belong to W. If there's a K is any scalar and U is inside W, then the scalar multiplication of K and U must also belong to W. So that means this is what we have to prove in order to prove that a certain vector space is contained within another vector space. So note that if V is a vector space, then V and empty set which is equal to 0 are subspace of V. So this is just the thing that you have to note. It's a simple statement. So if V is a vector space, then V and a phi which is a 0 I don't know if it's a 0 vector, are subspaces of V. So now no, these are other definitions. We just leave them as like that. These are other definitions. Let's look at the example of subspaces. So this is where we need to somehow focus. So examples of subspaces. So let's take the thing. If you let W be a set of all M22 symmetric matrices, so show that W is a subspace of the vector space M22. So let W be the set of all M22 symmetric matrices. Show that W is a subspace of M22. So we are required to show that W is a subset of M22. So now we need to prove those three conditions. So now, but we remember that we are saying that a M22 is a symmetric matrix. What is a symmetric matrix? It's a matrix that is a matrix is said to be symmetric. A is said to be symmetric if it's equals to its transpose. So in other words, now we say that A is symmetric if it's equals to its transpose. So the matrix A is symmetric if it's equals to its transpose. So its transpose matrix. So that's what we're talking about. So now let's talk about the solution of this. What we want to prove is that, remember, W is a set M22. It's a set of all 2 by 2 symmetric matrices. We need to show that W is a subspace of vector space M22. So given W being this set, it suffices to show that W is a subset of what called M22. Is a subset of 2 by 2 symmetric matrix. That is, W is a subspace of M22. So now let's go. So now we know that a matrix 0, 0, this matrix, it's any matrix, it's a 0 matrix. It's a 0 matrix and it belongs to M22. This is a symmetric matrix. A 0 matrix is a symmetric matrix. So if you let this matrix be a what called a 0 matrix, this belongs to M22, which means that W is non-empty subset. Remember, they say that W is what? Is a set of symmetric matrices. So that means W is non-empty subset. We proved the first what? The first condition. So the second condition, if we let A1 equals to A1 transpose, remember they say that W is a what? Is a symmetric matrix. So if we let A1, that means we're taking A1 and A2 be inside M22. That's what we are saying. So if we let A1 because it's a symmetric matrix, A1 must be equal to A1 transpose and A2 equals to A2 transpose B inside M22. Then we have the following. What do we have? The combination of these, because you know that if you take the individual, these, we need to prove that this is also inside what? M22. That's a closure property. It's inside M22. So that's what we want to prove. So if you let A1 equals to A1 transpose and A2 equals to A2 transpose, because it's a symmetric matrix, belongs to M22, then we have these. A1 plus A2 transpose, we can have them. This can be individual like this, A1 transpose plus A2 transpose. But A1 transpose plus A2 transpose, A1 is equals to A1 transpose is equals to A1 and A2 transpose is equals to A2. So this is just equals to A1 plus A2, which means it belongs to M22, or it belongs to W, because W is the set of 2 by 2 symmetric matrix. So this proves the closure property under a vector addition. This means that the closure property under VA holds. So now let's prove the last one of this example in order to conclude that indeed what called W is a subspace of what called M22. So now if you let K belongs to R, or the real number be any scalar, so then we have the following. We need to prove that these KA1 transpose, we need to prove that KA1 also belongs to M22, or just W is the same thing. So now to do this, we need to prove that this belongs to W, which is the same as M22, you know that. So now then if we let K be inside R be any scalar, then we have what to call K times A1 transpose. This is the same as K times A1 transpose. So, and remember, A1 transpose is equals to A1. That's why we have K times A1, and this belongs to what to call W. That's the same. That's the symbol thing. It belongs to W. Remember, A1 belongs to W. So that's the simplest thing. This means that the closure property under scalar multiplication holds. So now, therefore, we can conclude that this W is a subset of M22. Therefore, what to call in words, we can say that W is a subspace of M22. So that's how simple it is. So we can go to number B. And number B, that's how simple it is to prove that a non-empty or subset of W, the non-empty subset W of V is a subspace of V. So that's how we do it. So now suppose that A is an M by N matrix and 0 is the M by 1 0 column matrix. Let's consider the system of linear equations of M homogeneous linear equations in the unknown x1 up to xn, where these is interpreted as an element of a vector space Rn with the usual vector addition and scalar multiplication. So now what do we want to do? We want to prove that S is a subset of what to call so if we let S be, let's go to the solution, let's see. So if you let S be the set of all solutions of the system, let S be the set of all solutions of the system. So we want to prove that S is a subset of Rn. So that's what we want to prove. So now if we let S be a set of all solutions of the system, which is that, so then let X be this, be a zero vector such that AX equals to 0. such that ax equals to 0, then 0 belongs to is a solution. Remember, 0 is a 0 vector. That means 0 belongs to S, where S is a solution. It's a part of the solution, because always if this one is a 0 vector and we're multiplying A with this 0 vector, it means that these homogeneous linear equations will always be satisfied, will always get a 0 vector also. So therefore that means 0 is a solution of the system. So now when you go, if you let x and y be solutions of the system, so such that ax times ay equals to 0, because this condition must be satisfied according to the question, then we have this. Now we need to add the two. We have this a times, these are solutions x plus y. We need to prove that if we take these two individual elements, we need to prove that x plus y is also part of a solution. It's also the solution. So that's what we want to prove. So now, then we have this a into x plus y, which is equals to ax plus ay. This is equals to, remember this one is 0. This one will be 0 plus 0, which is equals to 0. What does that mean? If this guy is equals to 0, if ax plus y is equals to 0, it means that this one is a solution. Therefore, this will mean that x plus y belongs to S. So that's what we're talking about. It means it's a solution. Now, going forward with this, we need to, that means that's a closure property. That's a closure property. That's a closure property. So now, closure property under vector addition holds. So now, the last thing is to prove the closure property under scalar multiplication. So if you let k be inside a real number r, this was not supposed to be in bold, but just be r like this. Yeah, a normal r. So now let k belongs to r, then we have what called, if we let k belongs to r, we need to prove that kx, it belongs to S, is a solution to the system. So now if you let k belongs to r, then we have a into kx. So now we can take out k, then we just have, because this one is a solution, if I say it's a solution, that's a into kx, it's equals to k. We can take out k and put everything inside brackets. We've got k times k into a times x, but a times x is 0. Is 0, this one, according to the definition. So this is just k times 0, which is 0. Therefore, if this akx is 0, that means this guy, it's a what? It's a solution to the system. So kx belongs to S. That means k times x is a solution. That means the closure property under scalar multiplication holds. Therefore, we can conclude that S is a subspace, or is a subset of Rn. So that's what we are talking about. So that's how simple it is. Let's go to another example. Number C. We're doing many examples so that you can get the idea of what is happening here. Determine if the following are linear subspace. Explain your answer. If the given set is a linear subspace, show it, and if it is not, explain why. So we need to do this thing. Now, so Roman figure number 1, it's V equals to the set x, y, z such that 2x minus 3y equals to 0 is a subspace of R3. Is it a linear subspace of R3? If not, determine if the following are linear subspace, explain your answer. If the given set is a linear subspace, show it, and if it's not, explain why. So that's what they want. So now let's do the first one. So let's go to the presentation of the solution. We know the vector space that we're dealing with is given that V, it's a set x, y, z such that 2x minus 3y is 0 for what? Yeah, such that that thing is 0. So we need to prove that this one is a subset of R3. So now that's what we want to prove. So now let's go. Let's go. So we will prove the first thing, if W is non-empty subset or not. So if you let x equals to y equals to z equals to 0, because we know that x and y and z belongs to real number. So those are real numbers. So since these one are real numbers and 0 is also real number, so we can just let, these are any real numbers, x, y, z. We can just let x to be equals to y to be equals to z to be equals to 0. So therefore x, y, z, we have what goes 0, 0, 0. We have got 0 vector, and the 0 vector is inside R3. So that's what we're proving. We need to prove that it contains a 0 vector, and we have shown that a 0 vector also belongs to R3. So that means V contains 0 vector. So but we cannot conclude, we need to prove the other things, like the condition given 2x minus 3y must be 0. So 2x minus 3y equals to 2 into, according to this one, these are the coordinates x, y, z. So, or are the points x, y, z. What is what according to this? What is x? X is 0. This is 2 into 0 minus 3. Y is also 0. So this is just a 0 minus 0, which is 0. It's satisfied. So that means that condition is satisfied. Therefore, we can conclude that 0 belongs to what? A 0 vector belongs to V. That means V is non-empty. There is something inside V. So that's what we wanted to show. There's something inside V. So now let's prove the closure property under vector addition under VA. So if you let U to be x, y, z and let V to be x1, y1, z1 is inside V, such that this must be satisfied also. Because even 2x minus 3y is equals to 0, that means even 2x1 for this one, this one must be satisfied. 2x minus 3, 2x1 minus 3y1 must be equals to 0. Then we have this. So U plus V, for adding U plus V, it should be x, y, z plus x1, y1, z1. This is just equals to, we know how to add two vectors. We add the corresponding components together. So this is just x plus x1, comma y plus y1, comma z plus z1 as shown here. So now, since these x plus x1, y plus y1, z plus z1 belongs to real number, therefore the whole thing like this belongs to R3. So that simple thing, that in 3 dimensions, this thing belongs to R3. So now we have already proven this by concluding this, but we need to show the property that 2 of these x plus x1 minus 3 times y plus y1 is equals to 0. So let's do that, so that we can check also the condition. So this is 2 into x plus x1 minus 3 into y plus y1. This is just equals to, if you distribute 2 to each variable there, so this would be 2x, when we would say 2 times x, plus 2 times x1, which is b plus 2x1, then minus 3y, that is 3 times y, minus 3y1, that is minus 3 times y1. So then we group the like terms, we group the what we know. So that is 2x minus 3y. We know there's something that we can talk about, 2x minus 3y plus this plus, then we have this and this plus 2x1 minus 3y, which are these two. So then what is this guy? This guy is 0, and also this guy is 0 according to how we define V. So this is 0 plus 0, which is 0, and the condition is satisfied. Therefore, we can conclude that U plus V is inside V. That is a closure property under vector addition holds. Because also the condition holds. I hope this is clear. Let's go to the third condition. In order to conclude that V is inside R3. So if you let K be inside a real number, be any scalar, then we have what called K times U. That is K into, you know, U is X, Y, Z. So that is K into X, Y, Z. This is equals to, we know that when you multiply a vector by a scalar, we multiply each component by a scalar. So this will be K times X, which is KX, K times Y, which is KY, K times Z, which is KZ. We're multiplying here. So now, this, since these guys belongs to real number, it means that this thing belongs to R3. That's the simplest thing, because those ones are real numbers. That means also that thing belongs to R3. So now, this will be, we're left with proving the condition, whether the condition is satisfied or not. If the condition is not satisfied, that means we cannot put this conclusion, obvious. But we cannot put this conclusion, sorry, and then we cannot put this conclusion. So that's what we're talking about. Now, we have 2 into kx because it's the first element, minus 3 into, this is the second element, k times y. This will be equals to, we know we can take k outside of, as a common factor here. This will be k into 2x minus 3y, but 2x minus 3y is something, it's 0. So then this will be k times 0, which is 0. This is satisfied. So once it's satisfied, therefore we can conclude that k times u belongs to v. So the closure property under scalar multiplication holds. Therefore v is a linear subspace of R3. That v is a subspace of R3. So that's what we're doing. So now that's simple. We have gone through the first Roman figure, and we find that it's a subspace of V is a subspace of R3. So let's go to Roman figure number 2. Now we have what to call the following. What's the question? Let's go to the question. So U with this belongs to M22. It's a matrix with 2 rows and 2 columns, and the sum of the diagonals a plus b is equals to c plus d. This condition must also be satisfied. Don't forget that a, b, c, d belongs to R. So now this is the question. We need to prove that U is a subspace of M22. So that's the question. So that means we need to prove that U is non-empty, U is closed under vector addition, and U is closed under scalar multiplication. So that's what we need to prove. So now, solution, if you let A equals to B equals to C equals to D, this is the simplest step to do. So since this one is inside a real number, the 0 is also a real number. So that means we have A, B, C, D, which is just 0, 0, 0, 0, because A, B, C, D equals to 0. So this is a 0 matrix which belongs to M22. What does that mean? It means the first part is fine. What about the second part? We need to prove that 0 plus 0 is equals to 0 plus 0. 0 plus 0 is equals to 0 plus 0. This implies that 0 is 0. This is satisfied. Then it's fine. Therefore, we can conclude that a 0 matrix is inside a set of matrix U. Therefore, this U is non-empty. There is something. So now we're going to the closure property under vector addition. So if you let A be this matrix and let B be this matrix belongs to what? To U, such that this is satisfied, because it must be satisfied. Then we have the following: A plus B should be equals to A, this matrix plus this matrix. I told you that we add matrix of the same sizes and we add what called the corresponding entries. So now this will be A plus A1, then B plus B1, and C plus C1, and D plus D1. So then since this A plus A1, B plus B1, C plus C1, D plus D belongs to R, Therefore, this guy can belong to M22. Now let's show let's prove that the condition is also satisfied. So the condition is adding these together and should be equals to these added together. So that's what we are proving. So now it should be A plus A1 plus B plus B1 and what to call C plus C1, which is these guys, plus D plus D1. So now then we know that when we group this or A plus B, we got what called A plus B together, plus A1 plus B1, we get what called A plus B, A1 plus B1 together. So same applies to this one, we get C plus D together and C1 plus D1 together. So now we know that this A plus B is equals to C plus D. So if you let this A plus B equals to C plus D equals to X, and A1 plus B1 equals to C1 plus D1 equals to Y, because this should be true. Remember, according to these matrix A B, C, D, and the matrix A1, B1, C1, D1, this must also be true. So if you let this equals to this equals to X and let this equals to this equals to Y, then we just have X, this will be X, this will be X plus Y. It should be equals to X plus Y again, because this is X, this is Y, this is X again, this is Y, because they are equal. So this is satisfied. It means X plus Y equals to X plus Y. So therefore we can conclude that A plus B, or the matrix A plus matrix B, belongs to a set U. Therefore the closure under vector addition holds. So now let's go to the closure property under scalar multiplication and see if it holds or not. So now if we let K be a scalar, that's a scalar, it belongs to a real number, then we have what called K times A. Then we know what is a matrix A. Matrix A is this one. Then when we multiply matrix by scalar, we multiply each entry. So that is K times A, which is these. So that's a simple thing to do. So then since these guys, Ka, Kb, Kc, Kd, they belong to a real number. So therefore this whole thing also belongs to M22. That's a simple thing. But we also need to prove the condition, whether it's satisfied or not. So then we have what we call Ka plus Kb should be equals to Kc plus Kd. So now here we can take out the common factor of K. We should have K into A plus B. Also here we can take out the common factor of K. We should have K into C plus D. So this means that K and K can cancel each other because it's a non-zero. It's not zero, it just belongs to a real number. So it can cancel each other. Then we have got what we call A plus B equals to C plus D. So, and this is true according to the definition. This is satisfied. Therefore what we call K times a matrix A belongs to a set U. Then the closure property under scalar multiplication holds. Therefore we can conclude that U is a subspace of M22. So that's how simple we are doing this. It's a subspace. So now to the third Riemann figure. Let's go to the question and read it carefully. So W is this, it's a coordinate mx, my, it's a vector with two components where mx, y belongs to a real number. So we need to prove that this W is a subspace of R2. So now let's go to the solution. Let's go to the solution. So that's the thing. Remember, we're given W is mx my such that xy belongs to R. So now let's go. There's no any condition, it's just proving. So if you let x equals to m equals to y equals to 0, since this belongs to real number and 0 is also part of real number, so mx my, we have mxy, they are zeros, then you just have to substitute 0 times 0, 0 times 0, this is just 0 and 0, it's just a 0 vector 0, and this belongs to R2. So now it means that 0 vector belongs to W, then W is non-empty. That's the first thing, is satisfied. So let's go to the second condition, which is a closure property under vector addition. Let's see if it holds or not. So if you let U to be mx my, a vector, then let that other vector have the components, two components, m1 x1, m1 y1. So that's what we have. We're just changing the m's and whatsoever. That's a simple thing. Or m can remain like that, is the same. Even if you say m remain like that, there's no problem. So now if the m has to differ, then we need to do something like that. So it belongs to W. So then we have what called U plus V, which is mx my plus this. When I'm adding two vectors, we add the corresponding components. This is mx plus m1 x1, which is this my plus m1 y1. So since this mx plus m1 x1 and this one belongs to real number, it means that this already belongs to what we call R2. That's a simple thing. So therefore, what we call this guy belongs to W. That's a closure property under vector addition holds. That's a simple thing. So now the closure property under scalar multiplication. So if you let K belongs to R, be a scalar. So a scalar. So now then we have what call K times U. What is U? It's a vector with two components, mx my, that is K times mx my, which is just equals to, we multiply by K, this is just a kmx kmy, but kmx kmy belongs to R, which means that this belongs to R2. It's a vector with two components. Therefore K times U belongs to W, then the closure property under scalar multiplication holds. So therefore, if these three conditions are satisfied, we can conclude that W belongs to R squared. W is a subspace of R squared. So that's our conclusion. So it means that W is what we call subspace of R squared. So number IV, this is your homework to do. So now let's go and see it. Homework to do. So if you find it difficult, then you will let me know in the comment section. So let's go. Let's see what it means. And this will mark the end of the video. So then after reading this question, I will tell you what the next video will be. So then it will be talking, what is it going to talk about, or what is it going to be about. So IV, if you let V be a vector space and let W1 W2 be spaces of V, prove that the set U V says that V belongs to W1 and V belongs to W2. That is, U is the set of vectors in both W1 and W2. Prove that U is a subspace of V as well. So this is your what we call homework to do. So if you don't understand, you let me know in the comment section so that we can do it together. So but try it once. Let's see. Now this marks the end of the video, the end of our lesson. So we were just talking about what called subspaces. We talk about the definition of subspaces, and we talk about the theorem. We talk about how to prove that a vector is contained within another vector. We did many examples, several examples, and they're completely different, and they are approached similarly, but there are just some just have conditions that we have to prove. Some don't have conditions. They're very straightforward. So now the next video we're going to look at what called the Gauss elimination method, how to perform what called elementary row operations, and the what called reduction or the reduced row echelon form and the reduced row echelon form, so that this thing can help us to solve what called the system of linear equations. So that's what we're going to deal with. So I hope this video is very clear to you and it's very understandable. The content is that I'm distributing is very clear and very understandable. So if you find this interesting, you can support me by liking, sharing, and subscribing. So that's the only support that I want from you. Then just continue to do these videos to break this course into simpler pieces and simpler pieces of content. So thank you very much for your time. Have a wonderful day.